right. So just to get everybody on the same page, there are probably people in the audience that are not familiar with stream processing, right? So Ben, can you just give a definition of what is stream processing?
So to me, stream processing is having the ability to act on a sequence of events as they arrive, either as themselves or as in smaller groups, but in a continuous fashion. And this is kind of an important point of the term micro batching or nano batching is kind of orthogonal to what stream processing is, because even your network card does batching. It's called Nagel's algorithm. We do it for efficiency. So streaming in my case and stream processing in my case is all about doing it continuously. There's no stop start. There's no you don't stop stream processing to wait for a big chunk. No, instead you're continuously doing it. You might pull it in chunks for efficiency, but the continuous nature is the goal.
So if I'm understanding correctly, so it's all about triggering by events. It's always on, right? It's always incremental, always on. Right? Yeah,
that is the critical bit. So yeah, there's an ongoing kind of little thing, discussions in the communities where a lot of people are trying to look at these stream processing systems like Apache Flink, and there's a fun one saying, so how do I schedule it to start and stop? And the answer is you don't. You just leave it running, and as the event hits, you process it. And this is a bit of a shift to when you used to just wait till you had, a few gigabytes of data, press a button, and it would churn through. Not to say that approach is wrong, but the whole point of a stream processor is you don't have to do that. You just leave it running.
I think a natural question to ask is, it's if it's always on, it must be pretty expensive, right? So how do you manage the cost? Is it actually that expensive?
So this is an interesting question, and I'm going to caveat this by saying this is both my opinion and your mileage will vary, because specifics you can always engineer a scenario where things aren't true. But let's take the general case. Let's say you have orders to process. There's shipping orders. You're on an e-commerce website. Most of us are secretly e-commerce websites. Behind the scenes, we have people online buying stuff. So an order comes in and you want to process it. So the next thing you have to realize is, let's say you want to process this in a big chunk, every 5 hours, every hour, every day, right? So the first thing you've got to do is take those events as they land, and then you've got to store them. As you store these events, you're paying to store them. Then when you've got a big pile of them, you're then spooling up enough machines to process them within the time allowed. This is currently a big thing that happens in banks when you have this kind of a reconciliation step at the end of the day. The bank closes transactions and then churns through on a mainframe somewhere and does all this processing. This is expensive because you now have to have machines big enough to churn the backload in the amount of time you actually have
backfill data, right? And
exactly.
And batch.
That's the big batch. The flip side on streaming is the event hits, you process it as it happens. Yeah, you've got as long as you can take the throughput. So you now have to just say, I need to handle n events per second. And then as long as you can handle the throughput, you're only going to pay for the minimum amount of machines to handle that continuously. The two things about that are that, one, if the job fails, you failed on one or two events at a time. It's not a big deal. You just restart and go. There's no big downtime. There's not this massive crunch where on a lot of older school systems, if you fail partway through a batch, you've got to restart the batch. So instead, your amortized cost is quite low. In addition, you can often use quite small machines because you can just have them continuously going. If your demand ramps up, of course you're going to need more, but you'd need more on your batch side anyway. The reason to stream generally comes down to this. You need an answer inside a time window. That's a given. That's your SLA, right? I take an order from you. You probably want me to come back within a day to say, yes, it's allowed. You don't want me to come back 3 weeks later saying, I've shipped it when it arrived, a week after you replaced the order. So you kind of there's always going to be that trade-off. You can make things incredibly cheap in either direction, but generally streaming tends to be quite cost efficient because, one, there's no failure doesn't really cost you anything. All stream processing systems are built with this redundancy, retry, and all that kind of logic built in. Two, you pay for smaller machines, and you amortize the cost over a continuous period of time rather than having to pay for a spike. And three, you're never going to be without that data. So you're not storing it in large chunks in every single step of the way. So you're not waiting for answers. You're not going to have to hold more inventory because you didn't process an order. so you can save in other places as well. So on balance, everyone has shifted to streaming to both increase outcome, kind of the performance and value of outcome, but also because some of the older, bigger batch systems, right? They were really expensive because to handle, 300,000 records or 1 million records in a chunk requires a lot.
Yeah, that makes a lot of sense, right? I think a lot of the perception of, like why streaming is inherently expensive, runs all the time, right? It's actually working on the same amount of workload as you were, run it at the end of the day, right? We'll run everything all together.
Yes.
But a benefit is, failover, right? If you have a big Spark job that fails, right, you have to redo the whole process.
I
right?
wish
But
I didn't
with
know
streaming,
that so well as I do, but I've seen a few
Yeah.
big Spark jobs go crunch, towards the end of the cycle and then have to go, oh no,
Yeah.
oh no, what happened?
Yeah, some of it, has some of the failover built in, but not to a level that, with the
Yeah.
stream processing tool, right? You can have checkpoints and you can always, retry a very, very small amount of work you have to redo if something actually fails, right? And it's actually the same amount of workloads that's there, right? And also, there are a lot of questions at least in the Saros community, right? People look at stream processing and see it as a quite expensive, piece of tool, right? And how do I know if stream processing is actually useful for my business, right? Actually, the value overshadows, the cost. How do I know? Like, what do you speak, to those kind of users?
Okay, so let's kind of the reason I always come back to stream processing is actually to stop looking at the business for a second and start looking at their customers, right? Think in most cases, nearly all businesses eventually serve either directly or indirectly a customer, a person who has to do stuff, right? And as a user and a consumer of goods, the one thing I know is that I don't like waiting, right?
Yeah.
Right? How is it good? One of my favorite things about Uber is I know how long that car is going to get to come here. If it's raining outside, I don't have to leave the house or the building until I know the Uber's ready to pick me up. And I know for a fact that like when I place an order on Amazon and I know it's going to come next day, I don't have to worry. These are all done because these are all possible because of stream processing. So the fundamental thing comes down to if you're serving a user at any point in your system, whether it is a human or even worse, a machine that wants an immediate answer, you're always going to be limited by your slowest step in your journey. It's called Amdahl's law in programming, but it applies across the thing. The theory of constraint is the way it's often termed in manufacturing. So with stream processing as kind of a primitive to use at the bottom of the stack, there's less and less performance gates before you get to a user. There's nothing worse, particularly I find right now, as someone who has to fly around a lot, of I want to do something which requires an airline. The airlines always take hours to get back. It is painful. And I'm like unsure if my flight's booked, unsure if it's changed. And because they've not embraced streaming for various reasons, honestly, it's just the fact that they have such big systems, I think, and so much security that I, as a user, have to pay the price of their previous technological decisions.
Yeah, that is true. But the technology complexity, can you speak about that, right? So how do
Yes. So complexity is an interesting thing. Like, show me a simple system which can drive an interesting and rich outcome, and I'll be very surprised. Like everyone thinks, oh, but it's simple. I only do X and Y, and then you think, okay, wait a second. Let's think what does simple really mean for a minute, right? Now, the running joke I always say is more people build distributed systems than they think because a website requires your computer and mine, and we've already got a distributed system. So you think for a second, like, wait a second, what is actually simple? Because like most web things are built in minimum 3 programming languages as well.
Yeah.
And so that's kind of the first kind of obvious point of I always poke about complexity. But the next step is, what is the alternative to, let's say, bringing in a Apache Flink style stream processor, right? So you start with the ability to absorb events. That's great. There's a series of web servers. Now they got to scale. Okay, cool. So I put a scaling group against that. Now I need to make them reliable. Ooh. Now I fail over. I need state stores inside the servers. I need multiple layers to dump events. Okay, so now that's nearly always true. So now the event system that go on the back of that. So I need to be able to take events out. I need to store them, process them in either small groups to do some level of aggregation. I need to be able to filter events. I need to be able to scale and then do fault tolerance on these events. I need to have a timeliness factor, measure the SLA end to end. I need to handle back pressure. And as I keep adding these kind of fundamental features, because everything starts simple, it's great on day one. Day one, you could spool this all up. I know I have. I had end-to-end microservices all streaming gRPC between them. It worked great. And then I basically kind of put it into production and it worked fine. And as I put more and more load, and I had clients who also had SLAs, I had serious problems because as they rely on my SLA, right? If I have a problem, I need a system which is tolerant, which can handle that kind of fault tolerance, because I can't cascade that up the tree. I have to meet my contractual SLA. So I end up having to engineer things like failovers, things like checkpointing. And fundamentally, like, why should I be wasting my time building that on day one or day two or even day 50 when I should have almost thought, I am now doing stream processing. Should I have brought in a stream processing engine?
Yeah, you always use the right tool, right?
Exactly. Like, this is the kind of the big thing right now is we'd all love enough time in engineering to go and build it all from zero, right? It would be wonderful. We could guarantee it works. We could build a system tuned to the outcome we needed. However, show me, you're a product manager, tell me the last time you had enough time to build it exactly as you wanted.
Yeah. This
Never.
There's
always a trade-off. And
yeah.
we only have this kind of amazing technology because we're willing to lean on other systems. And the kind of challenge I often give to both my customers and other people I work with is, are we leaning on the right bits, right? Like, everyone leans heavily on gRPC because it's a very nice RPC system, but the streaming bits are bolt-ons. So it's like, why would you use a bolted-on streaming thing rather than a specialized streaming service?
Yeah. It all depends on the kind of workload that you're trying to run, right? And
Exactly. Yeah.
Always try to pick the right tool instead of the one that actually looks easy on the day one, but
Absolutely.
actually gonna when you go to production and try to scale, it doesn't work, right?
Yes.
Like true streaming is inherently easier to scale, is it?
So I'm going to say yes, and I'm going to provide a little caveat here, which is that scaling a system which can act continuously on events is how batch systems are scaled as well. So inside any batch system these days, right? Hell, inside Starox, right? You have your data is streamed from disk into the back-end services that do some of the crunches, then streamed to the front ends. So you can do these massive, petabyte queries. That is streamed already.
Yeah.
So even if you're doing that, and that's like a one-shot analytical query, sounds like classic batch, right?
Yeah.
No, it's streaming now because it's too big. The only way to get performance is to stream. The only way to handle very large systems and very large data is to stream.
Yeah, actually, when we do aggregation, we do a streaming aggregation whenever we can, right? To to not have like a hash table is too big, it doesn't fit into memory, right?
Exactly.
So we actually use that is a fantastic point that you just brought up. I mean, a lot of us are already using streaming without actually knowing it. So it's not really even that scary of a subject, right? Because we already have them in our production system, isn't it?
Exactly. Like I remember it was a different podcast, and Hannes, the creator of DuckDB, was talking, and he was pointing out that every single operator in DuckDB streams between them, right? And I was like, really? And then I went into the source code and looked at it, and I was like, wow, that's really quite cool. And then I remember reading the Starox source code the first time around. I was looking at how it sent data between operators, and I'm like, this makes sense. I now don't need a petabyte of RAM on my cluster. I have, in past lives and past jobs, and systems I can't fully talk about, but there were systems where you needed enough RAM to hold the whole data set. Some of those very fancy dashboards of yesteryear required, hundreds of gigabytes of RAM to run because they're the only way you could do slicing and dicing in real time on a dashboard.
Yeah. So streaming is just to summarize a little bit, right? So streaming is not as scary as it looks like, as the word looks like. Streaming does give a lot of value, but there are already many systems that we're using. You guys are using in production that are already streaming things around, right? Without you actually knowing. So with the technology that are available today, right? So what use cases can stream processing specifically excelling, right? What kind of use cases are there, for stream processing? If you can shine some light on that.
Oh, so I can say there are as many as we could invent, but let's just focus on a few to start with, and we'll see where it goes from there. So I'm going to start with one of the more obvious ones. So currently we're on a live stream, right? So there is connecting us to each other and to our audience right now there's a WebRTC stream which is called real time. I've forgotten now, but I remember when it was being launched because I was part of that team. Now, the WebRTC feed is a UDP stream of audio and video, and that's going through. There's a little bit of, and the processing you can see already on that is there's a blur on my background, and there's a blur on Sida's background. Now, that's part one. Part two is there's a chat here, right? A chat is an ordered sequence of messages coming from a lot of users being collated together and then being broadcast back out. This is done using real-time stream processing for many reasons. The first one is to be timely. Humans like to talk in a very synchronous fashion, right? But it's an asynchronous but synchronous. I say something, you say something, I say something, you say something. And although we can talk over each other, we make it feel synchronous. Now, the problem is that if it takes too long for that message to get back and forwards, right, the delay increases because of I send a message, you wait 3 seconds, then you send a message and I wait 3 seconds to hear from that. And it might take you 2 seconds to write it. That's a 8 second delay already.
Each interaction is adding up to the problem.
Exactly. So unless you're doing it continuously rather than batch send, you're going to end up with a terrible user experience to the point of where it loses all potential value. So chat is a big one. Now, it gets more interesting when you start having large numbers of people and you want to do moderation, because in a forum, in an open forum or one in the public space, you want to be able to filter out basically you want to filter out hate speech, you want to filter out anything harmful to the audience at large, because it's not fair to impinge someone else's experience. But also it's just a professional space, so of course we filter out tons of things. And I've definitely seen things where competitors' keywords are often filtered out in some chats. It's very funny when you see that happen. But the next thing is, of course, is chatbots. So these are things that aid us in some way. Those are things that have to act on a continuous stream of data, stream back results. It's all well and good to have a lovely AI agent somewhere, but if it took 5 minutes for it to come back, I'd get bored and go off the tab.
I think this is really interesting. I mean, the audience we have, we work on analytics, but stream processing also works in transactional systems, like you mentioned, right? Yeah. So, and what about in analytics, right? What kind of use cases, does it power?
Yes. So I, as you may have realized, I come from the transactional background. My background has always been like lots of things like payment systems, security systems, games, logistical things, logistics, where I literally was pick up a package, move a package, find a route. Now, on the other side, I have of course worked into the real-time kind of analytics, and here is where stream processing almost kind of like both comes into its own, but is also one of the most straightforward ways to add value. So this is something like this is when you start asking the questions of your system. And transactions is how you ask your system to do something. Analytics is how you ask questions of your system. So in this case, it's something like, how many transactions are we doing per hour? Can we afford to keep going at this rate? Are we going to run out of nuts and bolts in our car making factory? Should we slow down upstream production so we don't end up with what's known as work in progress? These are analytical questions because they require a look across more than one data point at a time. And this is the ability to say, I've got every single sensor streaming in. Are any of them exceeding a threshold of temperature for more than their standard tolerance? Or I've got people checking in rapidly right now at the airport. I'll be doing that later myself. And are we going to have enough people on the security gates to let people through? Do we need to open new security gates?
Yeah. So basically summarize, something like monitoring, right? Where the data freshness requirement is literally like milliseconds or 2 seconds, right? As fresh as possible for the machines, right?